In the previous video, we saw a chi-squared 1 distribution being used to test a hypothesis regarding proportions in two categories. So something as relatively simple as heads or tails. And we did this by calculating a Pearson statistic. So that was if my hypothesized proportion were correct, how many did I observe minus how many did I expect, squared that, divided it by how many I expected, and summed that over both categories. Now we're not going to prove it here formally, but I can extend the Pearson statistic to more than one split, so more than two categories really. And I can think of that really as, for example, if I hypothesize the proportion of each category when rolling a six-sided die, I could say two categories are how many sixes and how many not sixes. Then I could take the not sixes and say, well, of the not sixes, how many fives and how many not fives? And then I could take the not fives and say, of the not fives, how many fours and how many not fours? So I can effectively keep subdividing, and each time I divide, I'm adding effectively an extra degree of freedom. So if my null hypothesis has n proportions that I am claiming, then I've got n minus 1 degrees of freedom. Because if I've got two categories, then I've only got 1 degree of freedom. Because once I say 70% will be heads, inherently I'm saying 30% I expect to be tails. So if I've got n categories hypothesized, then I've got n minus 1 degrees of freedom. What we said on the previous slide was about when I had hypothesized proportions. I hypothesized 10 proportions, 10% in this category, 15% in this category, 5% in this category, and so on. And I could test how closely an observed data set agreed or disagreed with those hypothesized proportions. And if I had 10 categories, I had 9 degrees of freedom. But a more common use as well of chi-squared distributions to assess goodness of fit is looking whether, when I've got two different variables or two different factors, whether or not they look to be independent of each other. And so if I put this as a table with R rows and C columns, in fact, the row columns are constrained to certain totals. The column totals are constrained to certain totals. So in this case, I've got R minus 1 times C minus 1 degrees of freedom. So if I actually give an example of that, because that's fairly wordy and not totally clear maybe. Let's say that an insurance company records the colours of cars, red, black or blue, and records whether the drivers of those cars made a claim or did not make a claim. So these are two different things I could observe, the colour and the claim status. So that's what's observed. Now, for this case where I'm not hypothesizing the proportions, I'm not saying I think that red cars making no claims will be 20% of the data set, and I think that black cars making a claim will be 10% of the data set. We're not hypothesizing the proportions, but we are hypothesizing a different thing, which is that the colour of the car and the claim status are independent. Any chi-squared test that relies on a Pearson statistic involves comparing the observed values to what I would expect if the null hypothesis were true. So I need to know what the expected values would be under this hypothesis. So I need to say, if colour and claim status are independent, then the proportion of red cars multiplied by the proportion of no claim cars should be the same as the proportion of red no claim cars, and so on. So I need to work out the proportion of cars in my sample of each colour. So 400 of the 1500 cars were red, 600 of the 1500 were black, and 500 of the 1500 blue. Similarly, the claim categories 1200 of the 1500 did not claim, and 300 of the 1500 did claim. So if these rows and these columns were independent of each other, then the expected number of red cars making a claim would be 400 out of 1500 times 1200 out of 1500 multiplied by 1500. So if I work all of those expectations out under the null model, I would expect those counts. And again, if you want to pause the video at this time, please do, just to double check any of those. So what I want to ask is whether or not I would believe that these are independent based on that. Because any observed data set is unlikely to match the expectation exactly, but is the deviation away from the expectation too much for me to retain the null, or do I have to reject that hypothesis that these are independent? Well, I mean, if I look at the red column, the number in the red column is exactly what I would expect under the null, but I had a few more claims amongst black cars than I would expect if they were independent, and a few fewer claims amongst blue cars than I would expect if they're independent. But are those differences enough to reject the null? Well, I work out the Pearson statistic for each cell, so I'm going to have 6 of these observed minus expected squared over expected. So when I work out these 6 contributions to the Pearson statistic, I add them together and I get approximately 9.167, which is in fact beyond the 99th percentile. So I've got very strong evidence to reject the null hypothesis. Why is this a chi-squared with 2 degrees of freedom? Well, I've got 2 rows, 3 columns, so I've got 2 minus 1 times 3 minus 1 is 2 degrees of freedom. So even at the 1% significance level, I would reject the null hypothesis, and I would say the differences between what I expected and what I observed would be too great for me to continue to believe the null hypothesis.